the one I'm going to show you is bijective. It's not necessarily nicer because the bijection is a little complicated, but the other proof is not easy either. So, okay, so here's the bijection. I'm going to show it with an example. So we start with this n+1 cycle, and we write it so that n+1 is at the end, like in this case. Now the first thing I'm going to do is I'm going to look at the left to right maxima of this sequence. So I like so left to right maxima is in quotes because these are not really the left to right maxima of pi, but the left to right maxima of this cycle notation of pi. And then in each one of these places, I'm going to insert parentheses. And then, except for the last one, so I want this to have length 20 instead of 21, so I'm actually going to remove the n+1. And then I look at this permutation. Now, of course, this is a bijection, clearly. But unfortunately, it doesn't work because it doesn't always preserve the descent set. Okay, so it would be nice if I could just stop the bijection here. But for example, this 7, if you look at 7 and 8, in pi, pi of 7 was greater than pi of 8, but now since the image of 7 has changed, sigma of 7 is less than sigma of 8. And you can see that where the problem happens is exactly in the places where I inserted the parentheses. The image of 7 became lower and the image of 12 became lower. Everything else is fine because, well, the image of 17 changed from n+1 to n, so that doesn't cause any problem. But these 7 and 12 are the problem. So the second part of the bijection will be to fix that. So these pairs, like 7 and 8, that were descent in pi, but not in sigma or vice versa, I call them bad pairs. And now what I'm going to do is make some switches in sigma that will fix those bad pairs. Okay, so I'm gonna describe the bijection in general in the top, but maybe it's easier to just look at how it works in this particular example. So what I'm gonna do is I look at the rightmost entry of the first cycle, which is a place where something could go wrong. And what could go wrong is that 7, 8 and 7, 6 could be bad pairs because the image of 7 has changed. In this case, they are both bad pairs. If they are both bad, I'm going to choose the one that where sigma of 6 or sigma of 8 is larger. So in this case, sigma of 6 is larger. So 7, 6 is the bad pair that I'm going to fix first. So the way I'm going to fix it is just by switching 6 and 7 in this cycle notation of sigma. So this is the switch. Okay. So switching that actually fixes the bad pair 6, 7, and it also fixes 7, 8 because that's why I chose to fix 7, 6 rather than 7, 8 because now the switch fixes both. Okay, so that's good. The problem though is that some other things could go wrong now. For example, these entries preceding 6 and 7, there's this 1 and this 2. So pi of 1 was 7 and pi of 2 was 6. But now pi of 1 is 6, sigma of 1 is 6, and sigma of 2 is 7. So there was a descent that is not there anymore. And that's because the entries preceding 6 and 7 are consecutive. So what I'm going to do is just switch 1 and 2. And then I keep doing that. If this 20 and this 10 were consecutive, I would switch them, but I don't have to do it. Okay, so that's good. But there's another problem that could have happened. That's when I switch this 6 with this 7, I didn't check if this 6 with 5 was creating a bad pair. And in this example, it does. So I actually chose this example so it's like as bad as possible, so you can see all the switches that go on. Most of the time, I don't have to switch too many things. Okay, so this 6 and 5 turns out to be a bad pair. So again, I'm going to switch 6 and 5. Now I look at the preceding entries. If they are consecutive, like here, I switch them. Now the preceding entries 9 and 10 are again consecutive, so I have to switch them. And now I'm done. But now this 5 that I put here could create a bad pair with 4. So 5, 4 could be a bad pair. But okay, here it's not. So I'm done fixing everything that this parenthesis here messed up. Now I move on to the second cycle. I look at the rightmost entry, which is 12, and again, I look at whether that putting the parentheses created a bad pair, 12, 13, or 12, 11. So here 12, 11 is okay, but 12, 13 is bad, so I'm going to switch 12 and 13. Now I look at the entries preceding them, 6 and 8, but they're not consecutive, so that's okay. But now this 13 with 14, it could be a bad pair, which it is. So I switch them. I look at the preceding entries, 6 and 7, they are consecutive, so I switch them. Now the preceding entries, 2 and 1 are also consecutive, so I switch them. And now, okay, this is okay. And now the 14 together with 15 could have been a bad pair, which is this. So I switch them. The preceding entries are okay. And now 15, 16 is okay. And now we are done. Okay, so after all these switches, I end up with a permutation that has the same descent set as pi. So there are some things that are relatively easy to check. One is that this algorithm always ends, and that the descent set is preserved. Those are relatively easy. What's harder to show is that this is invertible, but it is. One can also show it's a bijection. Okay, so this is what we define as sigma of pi. This is the same permutations, but in one-line notation. So you can see where the descents happen. Sometimes there are positions where here I had a 9 and that became a 10, so it's not true that I always move the numbers down. Okay, so I think, yeah, that is all I wanted to say. Yeah. Okay.
Any question for Sergio?
Did you try to program the algorithm?
I did. I program it and
What way?
Both ways, yeah,
And
the
it works.
inverse and it works. And, yeah. It works for n up to like 20 or something.
Any other questions?
What's the worst case and the average case for the number of switches?
Well, I haven't studied that like precisely, but from I guess I could check with the computer how many it takes usually. But if I come up with a random permutation, most of the time I don't even have to make any switch, and sometimes there's a few. I don't know exactly. I would say worst case is going to be order of n. I think it's order of n, but it might be order of n squared. But I think on average it must be much lower than that.
Can you classify those that take the longest?
No. Actually, the way I found this one that takes a long time is just I ran a program by computer and I looked at a lot of switches.
Are there any conferences coming up soon about permutations and
So yeah, there's this conference. I know that it almost overlaps with a conference in China that some of you are going to. But I think technically it doesn't overlap. That starts before. Yeah. So if you're going to get really fast from Dartmouth to China, maybe you can go to both.
Let's thank the speaker. In the best interest of wrapping up things on time, I will call upon Professor Basur